All right. So, again, a couple of things. With the four major types of chemical reactions, you need to be able to identify them based on just looking at an equation. What is it? What does it look like? How does it operate? And then you also need to be able to identify them by looking at kind of what we did yesterday. If I give you A plus B yields AB, what kind of chemical reaction is that? If I give you A plus BC yields B plus AC, what kind of chemical reaction? Some of them are going to be straight up regular chemical reactions. Some of them are going to be kind of like yesterday where we showed you pictures and things along those lines to help you out. Make sense? What are the four major types of chemical reactions? Decomposition, synthesis, double and single replacement. In a synthesis reaction, what is taking place? Yeah. They're combining together. That's where we have 1 plus 1 yielding 2. Again, the arrow is representing yields or means to make. So this is where we've seen A plus B yields AB. That's a synthesis reaction. Both of them together combining to form one new product. When they combine together, what happens to all the chemical and physical properties of that new substance? They change. They have their own. So A had its own special properties. B had its own special properties. Now AB has a whole new set of properties that is completely different than A or B. What does the decomposition reaction then look like? John? It's exactly the opposite. So it's going to be AB yields A plus B. So this is where we take something big and we break it down into more simpler parts. I believe these two are the two that most of you feel comfortable with. Most of you probably can identify these. Most of you probably feel like, yeah, I got this, Mr. Arnold. Correct? All right. Let's take a look at single replacement. What's going on with single replacement? Lubna. So when a stronger metal is replacing a weaker metal, how does it look when we use our letters here, Lubna? If you take a look, what happens? We have A and C as metals. They are literally, C is kicking out A. Wait a second. See? So, all right, let me figure out how to erase. I totally just made a mistake right there. So, it should be A by itself and B and C now together. So, what's happened is we have A and C are our metals. C is kicking out A. A is now by itself. B and C are now connected together. You have one element replacing another element. Yes? Yes, we're talking in single replacements. It's a good question. Does it only replace the one in front? Yeah. In single replacement reactions, we're talking about metals. Remember, in ionic bonding, where do the metals go, first or second? They always go first. Those are the ones that we never change. So we're talking about ionic bonds. We're talking about keeping this guy here, A, or getting it replaced. A was the original metal. C replaces that original metal. And in fact, it should be, and that's my fault again, it should be CB because C is the metal that's getting replaced. So change that again for the third time. I apologize. It should be BC because B is the non-metal originally, and C was the original metal. So it is AB plus C yields A plus CB. A and C are the metals. They are switching. All right, so the last one that we actually have is going to be our double replacement. This is where we are switching partners. We have A, B, we have C, D, and how does it end up once we get done here? A and B were partners, C and D were partners. What's now going to be the partners? China. C and A are going to switch. So now we're going to have C and B together, and we're going to have A and D together. Again, all we have is the first element just swapping partners, switching over. A and B came into the equation together, but they left with different partners. C is now with B, A is now with D. Questions? The question again is, why do we need to balance chemical equations? Nate? The law of conservation of mass, which is what you guys were working on yesterday. It says that mass cannot be created or destroyed. It can only change forms or partners or whatnot from there. So when we have a chemical equation, and let's just simply use hydrogen gas plus oxygen gas, and that's going to yield what we all know as H2O. First of all, what type of chemical reaction is this? It's a synthesis reaction. We have two things going into one bigger thing. All right? So this is a simple synthesis reaction that we need to sustain our life. Now, by doing the RAP method, what we actually find out is how many reactants we have, how many products we have, and then what are the atoms that we are using. That's what the RAP method stands for. So we have and go ahead and draw this on your paper if you haven't done so already. The R is on the left side of the arrow. The left side represents what part of the equation? What's it called? It's what goes into the equation, which are called reactants. Thank you. A simply represents the atoms that we're using, and then the P is what comes out of the chemical reaction, which are called the products. Okay, so it's reactants, atoms, and products. So if you take a look at the atoms, let's start in the middle column here for the atoms. What atoms am I using in this chemical reaction? I'm using hydrogen and oxygen. So I'm literally putting the atoms right down the middle. I'm not putting H2, O2 or anything. I'm just, what elements are we using? What atoms are involved in this reaction? Now, on the reactant side, which is the left-hand side, how many hydrogen atoms do I have? 2. What is this little number called that hangs off down below the actual element symbol? It's a subscript. Sub meaning down or below. Script is telling us how many we have. So H2, the subscript, tells us that we have 2 hydrogen atoms. How many oxygen atoms do I have? 2. I have 2 as well. If we take a look on the product side now, we're going to move over to the product side. How many hydrogen atoms do I have on the product side? I have 2. Oops, let me change colors here. I have 2 there. How many oxygens do I have on the product side? I have 1 there. So, according to the conservation of mass, have I conserved the mass? No. Where's the problem? Lubna. I'm missing 1 oxygen. I went in with 2 on the reactant side, but I came out with only 1 on the product side. So somewhere 1 disappeared, and we cannot create or destroy. So we have to be able to account for all of that stuff. So, Mr. Arnold, how do we make this happen? We have to add what are called coefficients. Coefficients are big numbers that go out in front of our atoms or our elements, okay? If I put a 3 in front of a parentheses, what do I have to do to that whole system? Distributive property. I've got to multiply it all the way through. So it's not just x plus 2, but it's 3x plus 6. So a coefficient is like a big number out in front of a parentheses. It's going to be a big number out in front of one of our atoms. It is going to allow us to multiply through so that we can add atoms to the system. All right? So if I'm working on this, I can't just come in and say, well, Mr. Arnold, let's just put an O here. That doesn't work. The equation is written. Everything is good. What we need to do is add coefficients. So how many do I have on the product side? 1 right now. I want to get it up to what number? 2. What times 1 gets me to 2? 2. If I add a coefficient out in front, I can now start to balance my chemical equation. I noticed, Lubna, you have a question. Go ahead and ask it. We do not remove anything. We are going to leave it as is. However, the distributive property says that I have to carry it all the way through. So what I've done is changed a little bit about hydrogen. I have 2 water molecules, but inside of 1 water molecule I have 2 hydrogens, right? So if I take 2 times 2, that equals 4. I no longer have 2, I now have 4. If I take 2 times 1, I have 2 now, no longer 1. Mr. Arnold, that's great, but you messed up hydrogen. Can I easily fix the reactant side? Can I turn this hydrogen, instead of a 2, can I turn it into a 4? What do I add? I add a big coefficient, 2, out front. So that is 2 times 2, which we know equals 4. Now, take a look at your RAP table. Do you have the same number of atoms on the reactant side and the product side? Yes or no? Yes, you do. You have 4 hydrogens, 4 hydrogens. You have 2 oxygens, 2 oxygens. Look, the only way to create water is if I have 2 hydrogen molecules for every 1 oxygen molecule. Meaning, if I have just 1 hydrogen and I try to make water, it's not going to happen. I have to have at least 2. So 2 hydrogen molecules plus 1 water molecule will give me, oxygen molecule will give me 2 water molecules. This is the minimum needed in order for the reaction to take place. I have to have this many reactants, and I will produce this many products. Does that make sense? Yes, no? Maybe so? Okay.